Hello and welcome to the second tutorial in the T325, which is about the information storage. We're going to talk about three categories of media, storage media, which are the rotating media, the optical media, and solid state or semiconductor memory. So first let's start with an idea about why these different technologies can still coexist and why some category of technology does not override the other category. If we look at this brief comparison, we can see that each category of technology still has its own advantages that makes this technology surviving. So, for instance, the semiconductor memory is characterized by its simple construction, so there are no moving parts with all the mechanical problem that might arise from this aspect. And second, they have fast access times. From the other side, looking at rotating media, which are the which encompasses the hard disk drives and optical media. So, for instance, hard disk drive are characterized by their huge capacity with their reduced size, and optical media have the property to be the cheapest and most effective way to share data offline. So, every type of storage media has its own advantages compared to the other. So let's start first by the rotating media, in particular the hard disk drives and magnetic disks. So magnetic disks have what we call a ferromagnetic surface on which areas can be permanently magnetized. So the information now is encoded on this surface as a pattern of magnetism that can be detected, which is very important to read the information and thus make the information retrievable. So this is considered as a non-volatile medium compared to other volatile mediums such as the RAM, as you know well. And the next slide we're going to talk about how reading and writing operation are performed in such a disk. So let's start by the writing operation. In a hard disk drive, you can see that we have this arm with the read and write heads that are at the top, at the end of this arm. We have these concentric disks, these ferromagnetic disks, and the write head converts the electrical signals coming to the disk into a pattern of magnetism on the surface of the disk. So the read head does the reverse operation by producing an electrical signal based on the magnetic field which is found on the disk. So these two heads, as I mentioned, are assembled together and mounted on this arm that move gradually across the spinning disk, and the data, of course, are recorded in concentric tracks as you have seen in previous courses. So everything is about relation between electricity and magnetism. Let's have a look about this relation based on the experiments that have been done previously. So the first experiment result that's found by Oersted and Ampere is that any electrical conductor carrying a current has associated with it a magnetic field. So this is how electricity will produce magnetism. And from the other side, electrical, which is the Faraday's law, that electric currents could be produced by a magnetic field as long as the field was varying with time. So a varying magnetic field will produce electric current. So how can we apply these results on the hard disk drive read-write operation? So let's start first by writing, how writing is performed in hard disk drives. So in writing, we convert, as we said before, the electric signal into a magnetic pattern. So in order to do this, the write head must be an electromagnet, which shows this relation between electricity and magnetism. So in order to write the magnetism pattern on these small area on the disk, the magnetic field should be concentrated in order to be concentrated enough in order to magnetize the specific area permanently or until the next write. So the disk is rotating under the head and the head is moving. We should vary the current in order to write appropriate pattern of magnetism in the appropriate area. This will translate or corresponds to a stream of bits to be written on the disk. So let's have a look on the reading. So in writing, we are converting the electric signal into magnetic through the magnetic pattern through the electromagnet. Now reading operation will read the magnetism pattern and convert it to electric signal corresponding. In order to do this, we will use the Faraday's law, which is that a varying magnetic field will produce electric signal. So the disk is rotating under the head. The different magnetism pattern will corresponds to a varying magnetic field, which will be translated, this varying magnetic field will be translated into a voltage signal at the reading head. So the signal indeed represents the transition between the different magnetic state rather than the state itself, given that an unchanging state will not produce an electrical signal. The changing states, the varying magnetic field, which is our case, will produce the electric signal. So this read-write scheme was done up until the 90s. However, with the growth demand for larger data storage capacity, push towards having greater areal density, and at the same time the need for smaller diameter disks. So this requires the magnetic bits to be smaller. And the size, this restriction and limitation in size is indeed a limitation to the original read-write scheme, since a smaller magnetic bit will results in a smaller voltage signal, which will be then difficult to be detected against the background noise. Given that the size of each bit is smaller, we cannot apply a high voltage in this smaller space, because it will affect the neighboring areas, and thus the reading will not be accurate. And thus there was a need for an additional or alternative technologies, and the solution came with the giant magnetoresistance. In order to understand the giant magnetoresistance, let's start with understanding what is the magnetoresistance. A magnetoresistance is has the effect of a change in the electrical resistance of a conductor when it is placed in the magnetic field. So if we have a magnetized conductor, the resistance will be different than a demagnetized conductor. So how to do this? Usually this is done by measuring the resistance, and based on the measure we can decide that this conductor is either magnetized or demagnetized by applying a voltage and measuring the current. And we all know that the resistance is equal to voltage over the current. So the question is, since it is an easy to apply principle, why we did not use this? The issue is that we cannot have, in order to measure this variation of resistance, we need to apply a high voltage in order to be capable of differentiating the small amount of change of the current. So this is the limit of this principle, since applying a high voltage will overheat or damage the head. So this concept that was invented 150 years ago could not be applied because the change of resistance was below 1%, which cannot be detected using the limited amount of voltage that we can apply. The breakthrough came with the discovery of giant magnetoresistance, what we call the GMR, which such material has has the property to drastic change of resistance in response to the magnetism, which is around 50%, and which can easily be detected with the limited amount of voltage that we can apply. This was discovered by Albert Fert in France and Peter Grunberg in Germany, and they received the Nobel Prize of Physics in 2007. And the giant magnetoresistance is one of the first product of nanotechnology. Just briefly, we're going to define the nanotechnology, which is the characteristic that deals with objects with dimension order of a nanometer, which is 10 to the power minus 9. And many of the techniques used in nanotechnology were developed for the production of microelectronics. And as we said before, the GMR, the giant magnetoresistance, is one of the fruits of the nanotechnology. In order to increase the areal density, other techniques were also proposed, such as the perpendicular magnetic recording. So before starting, let's us explain the conventional recording, which is also known as longitudinal magnetic recording. You can see that the magnetic bit can be seen like a tiny bar magnet point along the track. This is why we call it longitudinal. In perpendicular magnetic recording, you can see that the bar magnets are aligned at right angle to the disk and point in and out to the disk surface. This allows us to put more magnetic bits in the same surface. However, it requires additional material that can be observed in the difference between the read and write head in order to cope with the smaller size, and we need an additional layer that will allow the transmission of the magnetic field between the two parts of the read and write head. So in order to have the smaller bar magnet or magnetic bit, we need the material to have additional property, which is the coercivity, the high coercivity. Coercivity by definition is a measure on how difficult a material is to magnetize or demagnetize. So if we talk about high coercivity material, which is a material that is difficult to magnetize but also difficult to magnetize, so we have to put a higher magnetic field in order to change the magnetism pattern for the magnetic bit or the bar magnet. But at the same time, once this material has the magnetism property, it will be very difficult to change it, and thus it will not be affected by the read and write operation from the neighboring bits. So now let's move to the second category of our storage, information storage media, which is the optical media. The second part of our lecture is about optical media. Let's start first by a brief introduction about this category. So the data is written on spiral track as a series of bits of various length. So this is the first terminology, the first term we need to understand as part of the optical media terminology. The second one, so first the series of bits represent the data. Second, we need to understand what is a track pitch, which is the distance between adjacent tracks. So if we look at this image, we can see that this is the track pitch. So third, the information are written in the form of a sequence of bits and lands. However, it's important to understand that bits and lands do not represent the ones and zero. However, the change between bits and lands represent this the ones and zero. So whenever we have a change from bit to land or from land to bit, this is interpreted as 1. As long as there is no change, so we are still in bits or lands, so this is read as 0. In general, an optical media consists of 4 layers. We're going to start from the bottom to the top. So this is the laser emitter. The first layer near the laser beam is the data layer, where the data is written and encoded. The second layer is the shiny layer that reflects the laser. The third layer is a protection layer to protect the shiny layer. And the fourth one is the artwork where we can print or write the information about the optical media. So this is in general the four layer constituting the optical media. So how the data is read: the laser beam is focused from the emitter on the track and reflected back. The reflected beam is then analyzed to detect the pits and lands, and thus deduce the values, whether 0 or 1, depending on the way we explained before. And there is always what we call a feedback mechanism or servo mechanisms, which includes optics, mechanics, and electronics, to ensure that the beam is focused on the track and does not drift away from the track. Just to put between brackets the difference between closed loop control and open loop control. In closed loop control, we rely on feedback to correct in case of error, while in open loop control we will have very sophisticated mechanisms to make sure that the error is minimized below a certain threshold. So applying the same principle we mentioned before, using pits and lands in rewritable CDs will not serve the rewriting mechanism. This is why the indentation used in read-only CDs cannot be used in rewritable CD, because in rewritable CD we need to rewrite or overwrite an existing information, and if we are working with indentation we cannot change a pit to a land and vice versa. So this is why there is a need for another or a different way, and this is done through using material with different reflectivity, and this is done through material that has two states or two phases, which are crystalline and amorphous. So one of these phases reflects light better than the other, and moving from one phase to the other phase is done by heating and cooling the material. So in this case we will have material that can exist in two phases. It is usually in one phase. By heating and cooling we can move it to the second phase, and then by doing another operation we can move it back. And this is the principle called by phase change recording. So by having different reflectivity characteristic of the material, by sending the laser and getting the reflected laser, we can decide based on the reflected laser whether the material is in the crystalline or amorphous, and then identify is it a pit or a land in our case, and thus we can read the data or the stream of bit accordingly. In Blu-ray and high definition DVD, the main difference is that the laser used has a shorter wavelength, and shorter wavelength allows the laser to be reflected on smaller areas, and thus we can focus the laser beam on a smaller spot compared to lasers with longer wavelength. So this allows to minimize the pits and the track pitch, and thus increase the areal density and the data capacity also. So the recording surface uses a phase change material based on the concept we explained before, and the pits are thus areas of contrasting reflectivity. The image shows the difference between the three types of media: the CD, DVD, and Blu-ray. The capacity, as you know, for the CD is around 700 megabyte. The DVD is 4.7 gigabyte, and the Blu-ray is 25 gigabyte. Comparing the numbers, you can easily remark that the track pitch is decreasing, and the pit length is also decreasing, and thus the storal density will be increasing accordingly. So these are other figures that shows the comparison between an audio CD, DVD, high definition, and Blu-ray disc in terms of laser wavelength, track pitch, and capacity in gigabyte. In Blu-ray disc, the tracks are physically spiral and not logically, while in the original CD the bits are led in the spiral pattern and not there is no physical spiral track. The track are written in a spiral pattern but on a flat surface in CD. In a Blu-ray there is a physical spiral track on which the bits are recorded. This is what we call a spiral groove. So the groove is used to guide the beam such that the bits are written in the correct spiral pattern. So we have two types of recording: the in groove, where the bits are recorded in the groove, or on groove, on the border of the groove. So there is again a servo mechanism or closed loop control that ensures the laser follows the groove, and it will move the laser from side to side to follow the wobble. And I will go back to let you see that the spiral track is not a spiral in the way we might think, but there is also a wobble in the groove, and this wobble, you can see it has a certain frequency or period of repetition. So the rate at which the laser moves is determined by the length of the wobbles and the speed of rotation, and as we said, the feedback loop is used to control the speed of rotation to make sure that the laser is still following the groove. This wobbling technique is also used to address 64 kilobyte blocks of data on the disk, and this will be out of the scope of our lecture, but is very important to read and the standard of Blu-ray, how this can be achieved. Briefly, the important features of Blu-ray disc are as follows. First, the data is held as a pattern of bits along a physically spiral track. There is a servo mechanism. The track produces a wobble signal because the groove has this wobble. This wobble information is used to locate blocks of data of 64K, and it is important there is an embedded or integrated error correcting code which is read Solomon in the Blu-ray disc readers. This allows to detect and correct the errors, and we're gonna see this in the third part of block 1, which is about error correction code. Now let's move to the third part of our lecture, which is the solid state memory. So we all know that the flash memory, which is the typical example of solid state, has an increasing storage capacity in the last years, and this follows the Moore's law approximatively, and the cost was decreasing accordingly. So we have variety of usage of the flash memory, such as the memory keys, cards, built-in telephone memory, etc. So why did we call this solid state memory? So we have two aspects. The first one, the term solid can be versus the term that is liquid or gas, vacuum tube, and electrons. So this is the first difference. And the second one, talking about solid state versus the rotating media or moving media. So these are the two aspects that from where the term solid came. One in the general context and the second in the memory context. So let's start with some foundations, some basics that I believe that you are familiar with. First, that we all know that the memory is comprised of ICs, integrated circuits. We have two sorts of main memory, the ROM and the RAM. And you know all the difference between ROM, which is read-only memory, and RAM, which is the random access memory. So the random access because that a data word in any location, the whole memory can be accessed as quickly as the data in any other location. So the access does not depend on the location of the data. And second, the RAM is volatile, so the power should be always connected in order to keep the information. And once the power supply is switched off, all the data stored in the RAM are lost. So on the other hand, we have the ROM standing for read-only memory. This is a non-volatile and usually used for programs needed on startup. So let's move to the evolution of the read-only memory with the programmable read-only memory, or the PROM. So PROM is a programmable, so which means that when it is manufactured, there is no data stored. It can be programmed by the user, but once it is stored, it cannot be changed. So we use the term programming rather than writing because it is done upfront before using it, while the term writing is related to the changes that can be done after starting using the material, the memory. So now the second step is about erasable PROM, or erasable programmable read-only memory. So as I said, programmable means that it cannot be changed when it is programmed. Erasable programmable allows to erase the PROM and reprogram it again. This is done through the exposure of the memory to the memory cells to ultraviolet light. The second step is the electrically erasable programmable read-only memory, or the EEPROM, where we can erase the EEPROM using an electrical signal rather than needing the ultraviolet light. Let's have a look on the comparison between the EEPROM and EEPROM. The EEPROM is cheaper than the EEPROM. However, we can only delete the whole of the device, while in the EEPROM it is more complex and thus the cost is higher. However, we can erase 1 bit or 1 byte at a time. So this comparison shows us that despite that EEPROM has this advantage of being able to erase 1 bit or 1 byte at a time, however the cost was too high. And this is where the flash memory came, which is a variation of EEPROM that with an affordable cost or acceptable cost and a density comparable to EEPROM has the features of the EEPROM. So the term flash is used to represent two aspects. The one related to the way it is erased, that can be done on the whole device on a certain block and can be done quickly in a flash. So let's have a look how everything is done, how reading and writing are done in a flash memory cell. So reading a cell is usually by detecting if the cell is in the state 0 or 1. So usually reading means if we read the content of the cell and identify if the cell is 0 or 1, given that a cell exists in one of these two states. When we erase a cell, we set all the bits to 1, and this is mainly related to the transistors used in the cell that we're going to see in a few minutes, few slides. And so when we erase a cell, we set all the bits to 1. And when we program a cell, if it is 1 and we're going to change it to 0, otherwise we keep it as is. So I will repeat, we have the state, erased state, which is all the cells are set to 1. When we program, we select the states that needs to be changed to 0. And when we erase again, we reset all the states to all the cells to the state 1. So as we said before, flash memory uses the semiconductor technology. This is why they are called also semiconductor memory. So the basic building block of the microelectronics is the transistor, and in flash memory it's important to note that every memory cell uses a single transistor. In other type of semiconductor memory, we might need several transistors to each single memory cell, and this is one of the reasons that allows the flash memory to have high storage density. So a transistor can be thought as a controlled switch. So a signal on the gate connects to the source to the drain. So if we apply a signal on the gate, it will close the switch and let the current pass from the source to the drain. This basic transistor does not allow the storage of the data, since once the electricity is removed or the signal is removed from the gate, the switch will be open again. So we need another type of transistor that allow to store a certain state that can be used later on to read the information stored. So the type of transistor that allow the storage of information is called the floating gate transistor. So this transistor has two gates, the control gate, which is similar to the gate we have seen previously in the basic transistor, and the floating gate where the charge that is to be stored is put. So the concept of reading and writing consists of either injecting a charge or removing the charge from the floating gate, this is for writing, or to detect if there is a charge or not in the floating gate. So to read the data, we apply a voltage on the control gate and see whether it succeeds in allowing current to flow between the source and the drain. If there is a charge in the floating gate, the voltage will be opposed to this charge, and this charge will not allow the current to be drawn, and thus we detect that if the current does not flow, this means that there is a charge and thus it is a zero. If the current flows, so there is no resistance in the floating gate and thus there is no charge and thus the cell is 1. We have varieties of flash depending on the details of the cell design, the configuration of the cells on the chip, and the circuits that accompany the memory cells. We have two types of flash memory, the NAND and the NOR flash memory. Briefly, we can list some comparison between the two types of flash memory. So first, one of the main characteristics of the NAND flash memory is that is optimized for bulk storage, while the NOR flash memory is optimized for storage of computer codes. So the smaller size of flash NAND cells allows to have a much larger capacity compared to the NOR devices. For instance, we can have 16:1 storage size. The random access time for the NOR flash is shorter. This is why it's used for the storage of computer code. In NOR we can program individual word, while NAND we can program pages at a time. The programming time is similar. It takes much longer time to erase a block in the NOR compared to the NAND. And finally, which is very important, is that the endurance of the NOR flash is 10 times than the NAND flash, which is around for 100,000 cycles, we have 10,000 cycles in the NAND flash. So in general, as we said, the NAND is optimized or used for bulk storage, while the NOR is optimized for computer code storage. In order to increase the capacity of flash memories, a concept is introduced which is about multi-level flash. The basic flash cells can distinguish between two options, charge or no charge, while multi-level flash can differentiate between more than two levels, and this allows to store more than one bit in each cell. And we all know that the number of levels is equal 2 to the power the number of bits. For instance, if we can distinguish between 4 levels, we can store 2 bits, 4 equal to the power 2. If we can distinguish between 8 levels, we can store 3 bits in each cell, and increasing the number of bits will multiply the the capacity of the memory. The memory is organized in a certain structure. So a memory might consist of a number of planes. Each plane consists of a number of blocks. Each block consists of a number of pages. Each page consists of a number of lines, and so number of words and number of cells. You can have a look at this memory data sheet to see the different characteristic of this memory. For instance, we have 2 planes in this memory. The page size is 4096 bytes. The block size is this. And you can see that we have this number of blocks times this number of pages and times this number of bytes.